Okay, let's now incorporate risk aversion into decision analysis, and let's also illustrate the difference to risk neutrality. So what is risk aversion? A risk-averse economic actor receives less absolute utility gains from a $1 increase in wealth than a $1 loss. And this is typically captured by a concave utility function, which is a utility function that increases at diminishing rates. So let's draw such a utility function. So we have an x-axis, and there we have typically something like wealth, and then we have the y-axis, and there we normally display the utility, but the shape of the utility function is concave, which means it increases at diminishing rates. So that means, okay, we have here the utility of wealth, which is like the square root of wealth. It could be also the log, but a very popular illustration is actually the square root of wealth. So now you can see at any given point a $1 increase in wealth gives you a higher utility, but the gain in utility is in absolute terms less than what the loss of $1 will be. So now let's do another example, and let's just assume that the initial wealth is, let's say, 9. And assume that the individual has a 50% chance of winning plus 7, so that would be 16. 9 plus 7, that's 16. And there's also 50% chance that the individual loses 5, so it drops down to 4. Okay, so now if we take a look at the respective utilities, which is the square root of the wealth, then here we have 2, the square root of 4, that's 2, and the square root of 9, that's 3, and the square root of 16, that would be 4. So now a risk-averse individual thinks in terms of expected utilities. So the expected utility is that the risk-averse individual expects with a probability of 0.5 the square root of 16, and with a probability of 0.4 the square root of 4. So that would be 0.5 times 4, so the first term is 2, the second is 0.5 times 2, so that's 1, so that's the expected utility of 3. So now what we can do is we can actually convert that expected utility back into a money equivalent by simply squaring the expected utility. So in this case, because the individual can expect the utility of 3, well, squaring it is the expected wealth or the money equivalent with it. So the money equivalent of the expected utility is 9, which is the square root of the expected utility. Okay, so that is the expected utility of 3, and the money equivalent would be 9. But now let's turn next to the risk-neutral person. So a risk-neutral person has a utility function which is a straight line. So this here was risk-averse. And now let's draw here maybe a risk neutral. And again on the x-axis we put again wealth. But now this is just a straight line. So the utility is equal to wealth. All that matters is the payoff. So in this case we would say utility is equal to wealth. Okay, so then if the current wealth is 9, and it could go up with a probability of 50 to 16, or with a probability down to 4, then the risk neutral individual expects with a probability of 50% 16, that's 8, plus with a probability of 50% 4, that's 2, so 8 plus 2, that's 10. So the expected, that shouldn't be, so the expected payoff is 10. Now here's the 10. So in other words, the risk neutral individual has a higher expected payoff from such a gamble. Okay, so now let's incorporate that into our decision tree. And so what we need to assume is an initial wealth. And if you remember, we first said, okay, if the individual litigates and the case is heard and the individual loses, it loses 63,000. So now here the green payoff is 75,000, the initial wealth, minus 63,000, that's 12,000. And if the person litigates and the case is heard and the person wins, it loses only 13,000, meaning the wealth drops from 75,000 to 62,000. And if the case is dismissed, well then the individual loses $3,000 of its 75,000 initial wealth, and we end up with 72. So now in order to calculate the expected payoff, or actually the expected utility, we have to focus on the wealth associated with it and then convert it into a money equivalent. So now a risk-averse individual, we assume that the utility function is the square root of wealth, and then the utility of litigation is, with 0.6 we can expect 12,000, with a probability of 0.3, 62, and with a probability of 0.1, 72,000. And then we get 167.26. So now what we do is, what is the money equivalent? Well, we square the 167.26, and then we get the money equivalent of 27,976. So in other words, the individual expects some monetary equivalent of litigation that is equal to 27,976. So in other words, every settlement that left the risk averse with more than 27,976 would be acceptable. Okay, so now what is that threshold? The only thing we need to do is, we know initially we have $75,000, and now we subtract the 27,976, and we are left with 47,024. So that means that a risk averse would settle at an amount of up to 47,000. Whereas if you remember in the previous example, the risk neutral, when we only looked at payoffs, they would settle at 42,000. So in other words, a risk averse person is willing to settle at a higher cost, because the risk averse person is so afraid of losing a lot and dropping a lot in terms of utility then. So to make a long story short, a risk averse individual typically has a lower money equivalent from any kind of a gamble where you can lose or win with certain probabilities than a risk neutral person. Okay, so let's stop here, and we will come back in other examples to the problem of risk aversion. But in the next problem set, let's just move to the problem of a principal agent problem.